talking about the second statement. So, but I'm again going to prove the opposite direction. Your problem set is going to ask you, not P and Q implies the other guy. And what I'm going to prove is the following. Not P or not Q implies not P and Q. So we start with not P or not Q. So this is assumption for conditional derivation. Here, I cannot split this sentence into smaller atomic sentences. Why is that? Well, because this is an or statement. It's not an and statement. All right? For example, Adam's question was nice. It's like, here, this is a totally different assumption. And so my logical deductions, therefore, will automatically, I mean, not always, but most of the times will be different. And so will lead to a different proof. So here, for example, we see that I'm stuck. I can't do I can't deduce anything from this argument. So what am I going to do? Well, remember, I want to show this, not P and Q. Always try to get rid of the negation sign. So therefore, deny the conclusion. So not P and Q. But that means assumption for indirect derivation. So I already have two assumptions. So that means I have two boxes. So now, at least from this, I can go one more step because this double negation of the argument 2. So I have P or Q, P and Q, sorry. I can go even further. I can say P and I can say Q because, this is AND statement. So this is simplification of the argument 3. Same here, simplification of the argument 3. What else? Okay, you know what? I can use another modus tollendo ponens. So here, remember, P is telling me that P is a true statement. Therefore, not P must be a false statement. But this or statement is a true statement. So if this part is false, it means this part must be true. All right? So therefore, not Q. This is modus tollendo ponens between the arguments 1 and 4. Again, you can say, why don't I use Q and this and get not P? Fine, you're going to get contradiction anyway. I'm not going to repeat anything because I have Q here, I have not Q here. So you see the contradiction. I see the contradiction as a grader, right? Or as a reader of your proof. So I close the first box. Assumption for indirect derivation box is now officially closed. From now on, I'm not allowed to use any of the arguments within this box. Don't forget that. So line 7, I'm going to say basically what I proved, which is this guy, negation P and Q. Okay, remember, I started assuming this guy and wanted to show not P and Q, which I already did. So I can also close, this is, by the way, indirect derivation between the arguments 2 to 6. Also, don't forget to write these. And then finally, in line 8, I'm closing the all boxes. I just write the statement that I proved. Not P, not Q implies not P and Q. So this is a conditional derivation between the arguments 1 to 7. All right? And that's it. That's how we prove this argument. Any question about this? Okay. Then let me jump to the third one. What is the third one? Okay, so again, I'm going to prove the opposite direction. P implies Q. Okay. All right, so once again, I'm going to start assuming not P or Q. And that's it. Because this is or statement, there's no way I can go further. Assumption for conditional derivation. All right. Remember, I want to reach this, P implies Q. I want to show P implies Q. All right. Again, this is just a side note for me. You don't have to put it. Well, what I can do, because this is another conditional sentence, I'm going to assume P, right? This is how we prove conditional sentences. Assume the first part. So this is another assumption for conditional derivation. And I want to show Q now. Very good. So I have two boxes. So once I have P and I have not P or Q, remember P is true, not P must be false, but because this is true, Q must be true. So again, this is modus tollendo ponens between argument 1 and 2. That's it. Remember, I wanted to show Q and I just showed Q. That's it. That's the end of my second box. So in line 4, I basically repeat my conclusion, which is P implies Q. By the way, remember, this is also what I did in theorem. I'm sorry, did this section 8 example 3 video in around minute 12. I had P, I had Q, therefore P implies Q. Remember? This is exactly it. Okay. What else? And then 5, remember I wanted to show P implies Q, which I did. So that means the entire argument is, the proof of the entire argument is done. P implies Q. Here I should write this is thanks to conditional derivations between arguments 2 and 3. Well, there's only 2 and 3, but this is conditional derivation between arguments 1, 2 and 3 and 4. All right, so that's it. This is how we prove this. One sort of hint, the opposite directions, meaning the arguments in your problem sets are maybe a little longer than this, and they will, at least few of them are going to require you to use previous arguments, which we did not need to use them. The opposite sides are well, easier, unfortunately. I wish I could do the other way around, but they are the problem set questions. But again, I mean, the proofs of those arguments are not going to be longer than, say, 15 lines or 10 lines. They're relatively short, and once you use them in the proof of theorem, your theorem proof will also be shorter. Yeah. Any question, guys? Okay, we have like 8 minutes. So what I want to do, let's come back to the reality a bit. Okay, so forget about those P's and Q's. Let's prove or try to prove something more, real, at least in math. Prove that square root of 2 is an irrational number. Okay? I don't know if you ever seen a proof of like this. This is sort of I don't know. That was our first proof that we did in our first year math course. My major was mathematics, and so that was sort of an abstract math course. A first proof we did, proof by contradiction. Sort of a standard proof approach. Well, obviously, what is this? Square root of 2 is an irrational number. This is like, I don't know, statement P, right? This is an atomic sentence, and it's P. So I'm asking you, prove P. Well, I mean, what? How? So in fact, this is an argument, but a lot of things are buried in this sort of in the back of this argument, which we omitted here, right? So most of the textbook, when you open it, it's going to say, prove that square root of 2 is an irrational number. But in fact, there are a lot of premises that you don't see in this statement. So and in fact, in our sort of econ courses, this is what's going to happen. It's like we're going to make a lot of premises already, and then we're just going to not ignore them, but we're not going to recite them again and again, or these premises. We're just going to sort of focus on the conclusion. And we're going to say, Nash equilibrium exists. Well, yes, but under what circumstances? So always there are premises. Don't forget that. I mean, yes, the theorems are arguments with no premise, but remember, if you have a P implied or these, these are theorems, no premise, but in fact, in a way, this part is a premise. If this is true, then this is true. If this is false, this is false. But I don't really care about these type of truth value cases. But if this is true, I need to show that this is true. So this kind of plays a role a premise would play. But here, there's even no such thing. Like, what assumption am I going to make, right? So, what are the premises here? Well, obviously, one premise is the definition of irrational number, right? What is irrational number? Or what if I want to prove by contradiction? So, proof by contradiction. So, we basically deny the conclusion. So what does that mean? That means not P, but what does it mean? Well, first of all, you need to know the definition of irrational numbers, right? Or the negation of irrational numbers. So as we know, a number is either an irrational number or a rational number, all right? So the set of reals, right? The set of reals consists of irrationals and rationals. And we know, again, these are actually premises, okay? So if you don't know the premises, of course, you can't prove the argument. And we know that these two are, in fact, disjoint sets, meaning irrational intersection rational is an empty set, meaning a number, a real number, is either a rational number or an irrational number. It can't be both, all right? So therefore, not P, meaning a square root 2 is an irrational number. The negation of this is square root of 2 is a rational number. So this is basically my not P. Okay? Well, another premise that I should actually know to prove this sort of theorem is, well, the definition of rational number. So what is a rational number? Well, a number is a rational number if it can be written as A divided by B, where A and B are actually natural numbers. Well, it doesn't have to be positive. Integers, and where B is non-zero. Oops, what am I writing? Sorry. B is non-zero. So this is the definition of a rational number, right? So therefore, if square root 2 isn't, so now I am making, by using this premise, I'm making deductions. Okay, I hope you see these steps. So the assumption that square root 2 is a rational number then means square root of 2 is equal to A over B, where A, B are integers and B is non-zero. Okay, next deduction. A is equal to B times square root of 2. Well, is this an inference rule? Well, kind of. In mathematics, we know that square root of 2 is equal to square root of 2 divided by 1. And we know that when I do the cross product, the equality sign is going to be still true. So I'm using inference rules, but we didn't really name them. So therefore, A is equal to B times square root of 2. Okay, I'm going to use another inference rule, and A square is equal to 2 times B square. All right? Well, why is that? Well, remember, if you have an equality like this, and if you take the square root of both sides, equality will not change. This is another inference rule, kind of, or premise, if you like to say, but I prefer to call it inference rule. So what does that mean? That means the following. Now I'm going to use another premise. If this is true, meaning square root of A is equal to 2 times square root of B, 2 times B square, which means A square is an even number. So this is a premise where you should be aware of. What is an even number? An even number, so a number is an even number if you can write it as 2 times k for some k, which is real. Okay, so that makes it an even number. So A square is an even number. Perfect. My next deduction is the following. A is an even number. Well, you don't need to know this. You can prove it, okay? Do we have time? Not really, but very shortly, how can you prove this? It may be obvious to some of you, but let's suppose not. So I am doing proof within a proof. So I want to show A is even. Given that if A square is even. All right, so how do I want to do that? Well, for contradiction, suppose A is not even. So what does that mean? The A is not even. So this is kind of a premise that you should remember. Again, a number is either even or odd. You can't be either or both, I'm sorry. So that means if you're not even, you must be an odd number. And what is the definition of an odd number? Well, a number is an odd number if it is 2k plus 1 for some k real. So therefore, let's say A is equal to 2k plus 1 for some k real. Well, in fact, I know that A is an integer, so k must be an integer as well. But anyway, let's leave that aside. Let's assume k is some real. So my logical deduction follows. Well, because of this equality is true, if I take the square of both sides, this equality should still be true. So that should be equal to A squared equals 2k plus 1 square. Well, again, if you open this up, that's going to be 4k squared plus 4k plus 1, right? So this is basically 2 to the power 2k squared plus 2k plus 1. So whatever this number, let's call it k prime, but A squared is equal to 2k prime plus 1. That means A squared is an odd number. But remember, my assumption was A squared is an even number. So I got a contradiction. So I close this box and say A must be an even number then. Okay? So that's a proof within a proof. All right, guys, so let's recover from what we did last time. So our claim was that, or the thing that we wanted to prove is that square root of 2 is an irrational number. All right, so we wanted to prove this by contradiction or indirect proof. So we denied the conclusion. So the negation of being an irrational number is being a rational number. So what does the definition of rational number? So square root of 2 is a rational number means that it's equal to A over B, where A and B are some integers and B is non-zero. Well, so let's suppose further that A and B have no common factors. All right, so in fact, well, a rational number can have common factors, right? For example, this could be, A could be, I don't know, 6 and B could be 8. But let's simplify them, all right, right? 6 and 8 we can simplify, and then eventually we boil down to A and some other A prime and B prime where they have no common factors, all right? So that's the idea. We can make this sort of further assumption. A and B have no common factors. You'll see how the role it's going to play. So we said if this is true, well then the next conclusion must be true. All we just did is a cross product. And then if this is true, we take the square of both sides and concluded that this must be true too. And well, if this is true, well obviously A squared is an even number because it's 2 times some number. So, and then we concluded A must be even. Remember, by contradiction, if A is an odd number, it must be 2k plus 1. If you take the square root of it, we proved that A squared must be odd as well, but it contradicts with the assumption that A squared is an even number, so therefore A must be an even number. And then, so that was the last point where we stopped. And then this conclusion actually leads to B as being an even number too. Well, why so? Well, you can directly prove it, or do an indirect proof, a sub-proof. But if A is an even number, it should be like 2 times K, where K is some real number, integer in this case. But if this is the case, when you take the square of both sides, it's equal to 4K squared. Right? Remember, a square is equal to 2b squared, so 2b squared. So this 2 and 4 will cancel out. We're going to have 2 here. So that means b squared is equal to 2 times k squared. So b squared must be an even number. But if b is an even number, similar here, b must be even too. All right? So what does that mean? That means a is an even number, b is an even number. What does that mean? If a is an even number, it has to be, by definition, equal to 2 times k for some k in R. And if b is an even number, it should be equal to 2 times k prime. K prime can be different than k, and k prime is a real number. But then remember, so this contradicts with this further assumption we had. A and b have no common factors, but actually they have common factors, which is 2. So that contradicts, all right? And so therefore, this cannot be the case. So remember, this assumption is denial of our conclusion. So our conclusion must be false. And hence, square root of 2, therefore, must be an irrational number. This is how we prove this sort of theorem or proposition in an indirect approach. And this is one way of doing it. Okay?